Hello everyone. Thank you so much for the nice introduction, Jake, and thank a lot for your help for making this talk possible. Really appreciate it, and thanks a lot everyone for coming here. I'm Dian. I'm a PhD candidate at Northeastern, working with Robotic and Robin Waters. And today I'm very excited to present to you guys about some of our recent works in Equivariant learning for robotic manipulation. As we all know, recently there has been tremendous success in using machine learning models for robotics. On the left, there's an example from Core 28 where folks at Google trained a grasping agent purely from real-world experiments. On the right, I have another example in locomotion where we can train a robot dog to how to walk, and again, purely in the real world using reinforcement learning. However, one of the drawbacks of such data-driven method is that machine learning methods are typically data hungry. For example, in the grasping work, it actually took folks at Google 4 months to collect 800 robot-hour data from 7 robots. This is apparently too expensive. It's not feasible in any small labs at ours. Or imagine that we are producing a household robot. It's hard to imagine that the robot needs 100 hours of training post delivery. So what we want here is to just have a single robot, maybe connected with a 3D mouse, and then to ask a dedicated grad student like myself to sit here for 800 hours. No, just kidding. Just for 1 or 2 hours to collect around 550 demonstrations. Or alternatively, we can perform reinforcement learning in the real world, but we want it to be done within a similar time frame, 1 or 2 hours. So the key question I want to ask during my PhD is how can we improve sample efficiency in robot learning to achieve this level of sample efficiency rather than training the robot for 800 hours of training. We want to really train it with just 1 or 2 hours within a reasonable amount of time. My key idea is to leverage symmetries in robotic manipulation. Let's imagine a simple example where the goal for the robot is to pick up the green trapdoor. Now imagine a different state where all of the objects on table are rotated by 90 degrees. What we want here for the robot to do is to perform the exact same grasp, but rotated by 90 degrees as well. In other words, those two scenarios are just 90-degree rotated versions of each other, but standard machine learning models will treat them separately as 2 different samples and train from them separately. This is very inefficient. We want to be able to generalize from the left scene to the right scene and to all of the rotated scenes from the same state. So what I really wanted to do during my PhD is to design algorithms that can automatically generalize over symmetries like rotations or transitions and so on. So throughout my PhD, we have been finding this idea in various problem settings. For example, we started from reinforcement learning, and then we did some work in behavioral cloning, grasping, pick place tasks, and so on. So we have been quite successful in using this idea in various different problem settings. And in the end, we also did something to solve symmetry mismatch, because real-world robotic problems are not always that perfect. Sometimes we may not have a perfect symmetric problem setting. And in that case, what can we do about it? So we experimentally, we have been very successful in that. So for example, in this very recent work that succeeded in Core 24, we were able to train a robot to finish a very complex bagel baking task. Here, the robot needs to open up the oven door, pull out the tray of the oven, pick up the bagel, put the bagel on top of the tray, close the oven. This is a very long time horizon task, but we only used 58 human demonstrations to train this task. Not only that, our model were able to solve multiple complex machine tasks, all within a relatively small amount of data. Rather than training the robot for 800 hours, we were able to collect all of those data in those tasks within 1 or 2 hours. So in today's talk, I'm gonna talk about how can we achieve this level of sample efficiency. I'm gonna start from some method in equivariant reinforcement learning, including equivariant actor-created method and equivariant Q-learning methods, and then talk about how can we extend this equivariant learning idea to diffusion policy, which is a very recent work that's very popular in robotic manipulation. In the end, I'm going to talk about how can we handle symmetry mismatch. Just as I said before, real world problems might not be that perfect for us to apply symmetric or equivariant machine learning models. What can we do about it? And now let's just get started. So first, in order to use equivariant learning in robotics, we need to think about what symmetry actually exists in our problem, right? So imagine that we have a robot that's in front of the cube, and we want the robot to push the cube from top to bottom, right? So we were in the state S, and we can execute an action A and reach the next state S prime. This is a transition in reinforcement learning. So now let's imagine the state is rotated by 90 degrees, right? So both the object and the gripper is rotated by 90 degrees. And we have a new rotated state G dot S. Now, if we also rotate the action that the robot executes, meaning before we were pushing from top to bottom, now we push from left to right, we will end up with a new state S double prime. But if you look closely, S double prime is actually a rotated version of the state S prime. So in other words, there is this symmetric property that exists in the transition function in robotic manipulation. If we apply the same rotation to the current state, action, and next state of the transition, the transition probability will not change. Similarly, this invariant property also exists in the reward functions. Imagine that we are not pushing a block. Imagine that we are pushing a piece of trash, and we want to push it out of the workspace of the robot. The reward that we will get from pushing it from the left state to pushing it on the right state should also be invariant to rotations. So in our very first Accelerator 22 Spotlight paper, we define a class of MDP that we call group invariant MDP, which satisfies those two assumptions, meaning both the transition function and the reward function are invariant to rotation. And then we can further prove that once you have those two invariant properties, the optimal solutions for the MDP is also going to be rotationally symmetric, meaning your optimal Q function should be a group invariant function. When you apply the same rotation to your input state and action to the optimal Q function, the Q value should not change. And the optimal policy function should be a group equivariant function. If you apply a rotation to the input state of your optimal policy function, the output action should rotate accordingly. So we further think about, okay, so since the optimal policy function and optimal Q function have this property, can we inject or enforce this symmetric property inside neural network architecture instead of asking the network to learn from the data directly? So we propose equivariant stack, which enforces this property using neural networks. And how do we do that? Luckily for us, there are some existing equivariant neural networks that we can use directly. For example, this is a steerable CNN from folks at UVA. So basically, what this network can do is that if you compare that with a conventional CNN, where you may rotate the input, it's not guaranteed that you get a rotated output. The equivariant convolutional network can guarantee to give you a rotated output when you rotate the input. And we can just leverage this type of constraint equivariant networks in our problems. So due to time constraint, I will not talk about the details of the architecture, but I guess many of you guys already know about it. So if you're interested in learning about the detail, I'm happy to talk about it after the talk. After having this architecture, there's another problem that we need to solve before actually applying it in our problem, which is how can we...
When you learn the either the reward or the transition function, and you have action as an input as well.
Yep.
You have the image, but you also as a state.
Yep.
And you have also the action.
Yep.
In addition.
Right.
You cannot apply exactly the same network in the image and the action. You have to do something different for that.
Oh yeah, that's a great point. So Yes, so here, I guess I'm only showing an example where, the output image can rotate when the input image rotates, but the same network can also process vector data. So a vector, in my opinion, is just a special case of an image. It's just a 1-by-1 image. So we can use a similar method once we define how the group or how a rotation should transform our image or transform our action. We can just embed it as a 1-by-1 image, multi-channel 1-by-1 image, and send the action to the network in that way.
And then you operate for a while just on the 1-by-1 and then connect it with the image, like the way we do it, like PointNet.
Yeah, exactly. So specifically for this Equivariant stack network in the Q network, we first have an Equivariant image encoder that takes in an image and generate an Equivariant embedding for the image, which is a vector or a 1-by-1 image, and we concatenate the action from there. So the image is already compressed into 1-by-1, and we can then concatenate the vector, which can also be turned into a 1-by-1 vector.
Okay.
Thanks a lot for that question. Yeah, so we have this tool, but we also need to define how a group element or how a rotation applies to the state and action, right? So what we do here is that we first define the state as a top-down image centered with respect to the gripper. Why do we do that? That's because after we abstract the state as this, we can define the rotation of the state as an image rotations. That was to use the Equivariant network that we discussed in the previous slide. We further define the action as the delta movement of the unit vector containing the delta x, delta y, delta z, and delta theta, which is the top-down rotation. And then we can define the rotation on the action being rotating the xy component of the action and leaving the other action components unchanged. So after we have this, we can just use the tool that, the E2CN or ESCN package to implement an Equivariant stack algorithm. And we got a great benefit from sample efficiency. So in this slide, we are comparing our Equivariant stack with the conventional stack, which is built using standard CEN. On the top left of each experiment, you can see the number of steps that we train the model and the success rate of that model. So our Equivariant stack were able to solve this floor opening task within 1,200 steps of training, where with just the same number of training steps, the conventional stack can only get a 20% success rate.
Will you subtract the manipulator from the picture?
Yeah, that's a great point. Yes, we did. So if you recall, in the state representation, we actually just remove the arm. So in simulation, we can just make the arm transparent, but only keep the gripper. In the real world, what we could do is we can take the point cloud of the scene, and then since we know where the gripper is, we can just remove all of the points above the gripper. And that way we will only keep the finger in the scene, but remove the arm, remove the occlusion.
Why is the gripper state part of the image on some level? Like I thought we were sort of thinking of the gripper as the action.
Yeah, that's a great point. The reason for keeping the gripper in the image is because we want to see the interaction of the gripper with the objects. So without that, for example, you won't know whether your gripper is open or closed, or whether you are holding an object or not. So it's easier to have the gripper as part of this info image.
Thanks.
But you definitely need it for the reward, right? If the gripper goes closer, you don't have any other idea whether the grip. You don't use any state. So you don't use any joints from the robot as a state.
No, for this work, no. But for the reward, our model are not predict. You mean like for the Q function?
Yeah. You predict directly. You don't need the reward.
Yeah.
Yeah. This shows my ignorance in reinforcement learning.
No. So, but that's a good point. So, when we think about building a Q function, we need to think about like whether it can estimate the Q value in all of the possible states. So we do need to think about, just from this visual info, can it recognize the success state or not? So in our case, since the image is always centered with the gripper, so for the task that we were testing, this image is enough. But there are definitely some tasks maybe it's not enough. For example, one object can be occluding another, or maybe we need the gripper to be interacting with the object in a specific way. Maybe this type of representation is not enough. In the actual diffusion policy, I will talk about another visual representation which uses the voxel grid, which contains a more complete information. But for the time being, this one, the top-down image is enough to predict the Q value. Great. So we talked about how to encode detection. We talked about this experiment where we can learn faster than the conventional stack algorithm. And quantitatively, we show the learning curves comparing our equivariant stack in blue versus some of the state-of-the-art reinforcement learning algorithms back in 2022. And we were able to see that most of them were not able to solve those symmetry tasks. This is mostly because the tasks are sparse reward. So you only get a positive one reward when you finish the task. And since the action space is a delta motion of the gripper, you need multiple action steps in order to get the reward. This is a quite challenging task. And our method were able to, just learn very quickly, but the only baseline that we're able to learn from some of the tasks is the firm baseline, which uses contrastive learning to learn a better visual representation. And another thing to notice that's comparing the blue line, which is on top, versus the green line that's always at the bottom. The only change that we did is to change the network architecture from a standard network to an equivariant network. So this is a great improvement in sample efficiency with a very simple change in the framework. Yes, please.
Do you? I mean, I know that there's value to having the equivalent architecture baked into the network itself, but do you have examples of results where you compared it against deliberately creating kind of augmented versions of the data,
Yeah,
capturing also these same?
Yeah, that's a great question. So so from my perspective, data augmentation can be applied at the same time with equivariant network. So for example, your equivariant network might only be symmetric towards like a subgroup of all of the SO2 rotations. For example, you might only be equivariant with respect to 8 discrete rotations, and then you can use the rotation augmentation to fill in those gaps. So actually in those experiments, we combine data augmentation with equivariant network. And we did have an ablation study where we compare using equivariant network with just doing data augmentation on a standard network, and equivariant network always wins. I think the reason behind this is that imagine that we are learning a ground truth function that is symmetric, right? So for a standard network, in order to really match up with the ground truth function, you need to learn the symmetric property that's inside the ground truth function. But using data-driven approach, like if you just use the augmentation to learn it, this is not guaranteed. But with an equivariant network, it's gonna be guaranteed.
Sure.
So it's not just that you don't need to spend effort to learn that symmetry, it's also that it's gonna perform better because one way the augmentation is not guaranteed, but equivariant network, it is guaranteed.
Yeah, it will only be approximately true, and the extent to which it will be approximately true will be dependent on how much data augmentation you do, etc.
Yes.
At some point, it's definitely easier to bake it into the architecture if that's possible.
Yeah. And another thing is that in order to perform data augmentation, this type of data augmentation is not like the standard ones, like random prop, right? For example, random prop you can basically apply to any problem, but for rotation data augmentation, we really need to think about how the rotation should apply to any part of my input and output and perform data augmentation accordingly. So this is similar to the process where we design the equivariant neural network. So I would say, there are like multiple ways of achieving equivariance.
Sure.
So if you use data augmentation to achieve it, I think it's also like part of the idea of using symmetries in those problem settings.
Yeah.
Thanks. That's a great question. We got asked about the competition that reverse a lot, basically in every paper that we submit to. And on top of the three simple experiments, we also tested the method with some more challenging pick place tasks. And in those more challenging pick place tasks, none of the baseline were able to solve them, and then our method was the only one that could solve those problems. So those results were very exciting for us, but those were only in simulation. So in our following core planning work, we applied this idea in the real world setting where we just perform on-robot reinforcement learning. We consider those 4 different tasks: block picking, block pushing, clutter grasping, and block involve, which is a pick place task. And we want to train a policy directly from the real world from scratch. So there will be no transferring, no pre-training simulation. We just directly train our Equivariant stack in the real world. So it ended up working very, very well. So for the first 3 tasks, we were able to solve the training within 45 minutes for an hour of wall clock time, which is significantly faster than 800 hours. But for the last type, blocking ball, we needed 2 hours and 40 minutes to solve it. That's mostly because this is reinforcement learning, and we need to reset the environment after each trial. So the blocking ball involved like 2 different objects, so resetting them took a lot of time. We also compared our method with the best performing baseline from the simulation experiments in the real world. So both of them were all trained directly in the real world, and our Equivariant stack were able to outperform this form baseline by a significant margin.
So can you tell us again how many networks do we have here?
We have 2 networks, one for the actor, one for the creator.
Okay.
Yeah, just a standard actor created architecture. We didn't have any other stuff. So the only thing we need to change here is to change the model architecture from a standard network to an Equivariant.
In all these cases, the equivariance is SO2?
Yeah, that's a good question. So in the previous paper, the symmetry is in SO2. We implement a C8 symmetry in the network and use augmentation to fulfill the others. In the real world, we extended into O2 because a lot of times the flip, if you flip the word, you should also flip the connection. So we also added the flip symmetry there, and the network was in D4 that contains 4 rotations and flip, and then we used rotation augmentation to fill in the gaps.
But you probably meant to be illustrated after.
Yeah.
That's a good point. So there are a couple of reasons that we didn't do 3D. First, I think if we use 3D symmetry, there will be a lot of symmetry breaking factors like the gravity. Sometimes we can ignore it. For example, if we are doing grasping, we can ignore gravity and just assume that we have enough friction on the gripper to pick up the object, so that we only need to consider geometry. So we did have 2 works that explore using SO3 symmetry in grasping. But for standard manipulation tasks, whether a task has SO3 symmetry, to me is not very, very clear. Because most of the time we will be operating on top of a table. The table itself is not going to rotate, and the objects always have their own canonical poles. For example, if we are manipulating an oven, the oven is not gonna, do random rotation. So there's a trade-off between the level of symmetry that we use versus whether the symmetry match to the ground truth function, because injecting SO3 symmetry is a very expensive procedure. We need to have much larger network and train is with longer time. So far we were only, in this paper, we're only considering SO2 groups.
But I think I remember you mentioning that you're going to show us some examples of results with voxel-based states.
Yeah. We will have it later.
Yes.
And this is an example of the training process. At the beginning of training, in reinforcement learning, the agent just perform random acceleration. This is resetting the environment because we don't want it to be stuck in the same state for too long. And after a while, it finally grasp the first object, and starting from that successful experience, we gradually learn how to pick up objects. And we can see that, just after a while, it can very robustly pick up all of the objects in the tree. And the whole process was within 1 hour of workload. Okay, this is the Equivariant actor-fitted method. And in the second part, I'm gonna talk about another Equivariant reinforcement learning method using Q-learning. So basically here, instead of using the delta pose of the gripper as an action, we use the final goal pose for the effector as an action. The difference between those two frames, those two words is, in my mind, is open loop versus closed loop. In the first case, we have more feedback along the movement of the arm so that we can adjust our action as needed. But for this one, each action is more, it represents a longer trajectory for the arm. So we can potentially do more challenging tasks with this richer action representation. So basically the procedure here is that we will have a top-down image of the scene, and then we're gonna need to select the XY target translation and the top-down theta rotation of the effector. So what we need to think about here is that given this type of framework, how does the symmetry exist in this type of problem? So this is the architecture that we use in this. Sometimes we call it pixelized action space or spatial action space. Basically, you have a input top-down image of your work. You send it to a cube. You send it to a cube network, and you ask the cube network to give you the cube values for all of the possible SC2 actions. Meaning, for each pixel in the Q map, it represents a specific peaking position. And for each channel of the Q map, it represents a specific peaking orientation. So if the object is here, the optimal grasp would be like this. That's why here we have the highest Q value, right? So now imagine a rotated state where the input image is rotated. What should happen to the Q map? So first, all of the Q maps should rotate accordingly, right? Because the object is rotated, so we want all of the translation to rotate accordingly. But that's not it, because what was originally 0-degree rotation is now 90-degree rotation in the rotated state. What was originally 90 degrees is now 180 degrees, and so on and so forth. So what should happen here is that the order of the Q maps should permute cyclically like this. This is the so-called, we can say it's ground truth symmetric property that we want in the Q network. And we can find the correct way of embedding this symmetry in the Q network to improve the sample efficiency dramatically.
So are you only dealing with the axis aligned grasps in this work, or?
The axis aligned, sorry.
Yeah, I mean, the grasps don't have to be only this, right? They can also be this, for example.
Oh, right. So in practice, we consider 8 different orientations from 0 to 180 degrees. So it's finer than that, but this is just the illustration.
But can you formulate it for continuous as well? Or not?
Oh yeah, that's a good point. I think so. Right now, I think this permutation property of the Q maps, I think it only exists with finite number of orientations.
Why? You can shift, if you shift on the circle, you get the same effect.
Yes. But I guess in that case, we will need to sample from a continuous signal. And because sorry, I think it's limited in discrete because we are doing Q learning. We need to perform argmax in the end to select the optimal action. But if we have a continuous rotation, we're gonna need to, I guess, first sample rotation from the continuous signal and then generate this translation map. And it's not gonna be the standard Q learning, right? So it needs to be, for example, the actor-fitted method. Yeah, it needs to be actor-fitted methods.
But if you have a steerable,
yeah,
function as an output. So
Yeah.
You can have a continuous function of the angle as a really output to be a continuous function.
Yeah, that's
And in that case, we can even like find the, because the angle appears in terms we know, we can even take analytically the minimum.
Yeah, I see. That's a good point. We haven't thought about that. We can chat more about whether we can, try to implement that. I think the discrete rotation is definitely a limitation of the work. But practically most of the time it is enough. So I think we tried 8 rotations ranging from 0 to 180 degree, or 18 rotations ranging from 0 to 180 degree. It is somewhat fine enough for us, for a standard grasping or pick place task. But if we are thinking about like some fine manipulation, I believe we would need some continuous rotation.
This is kind of tangential, but like in your real world experiments, you're relying a lot on like doing this re-rendering from this top-down view.
Yeah.
I don't know, I don't remember in your video if you had like external camera and like wrist mounted, but how significant is like there's some symmetry breaking due to like self-occlusions depending on the viewpoint, like where the robot arm is, and how significant is that for like the data efficiency?
Yeah, that's a good question. So first, for this approach, we actually don't have any symmetry breaking, because we take the observation before the arm moves, right? So we take the action after the entire trajectory finishes. We will take a new observation. So
So then you move the robot out of the
Exactly.
every time.
yeah, so in the previous section, in the SAC algorithm, we do have that problem. So typically what we do is we have at least 2 cameras looking at the slide, and then synthesize the point cloud from
Yeah.
those 2 cameras.
Gotcha, thanks.
Sure. Great. Okay, so similarly as before, we tested it with a bunch of environments. So those tasks are harder than the ones that we tested in SAC. This is mostly because each action represents a longer trajectory, it's a pick or place action. But we have a similar observation where our method is dramatically faster and better than the competitive method. And moreover, if you compare the green line and the blue line, the only thing that we did is changing the blue line standard convolution network into an equivariant. It's just a simple change that leads to this dramatic improvement. And
what was the reward you were using in real world?
the reward?
Yeah.
Yes, the reward are all for the first 3 tasks, the reward is sparse. You only get
the
a
real world experiments.
real world.
Yeah, for the grasping experiments that you were doing in the real world.
Yeah.
How did you get rewards?
You get a positive 1 reward for each successful grasp. So we can detect that by first reading whether the gripper is fully closed.
So
And-
you have some automated instrument.
Yes.
And it's just it's a sparse rule.
Yes, sparse reward. You only get a positive 1 reward at the end of the episode. Great. So furthermore, we apply a similar idea in grasping. I guess some of you might have been to ICRA 22. I don't know if you have walked over the exhibition area. There is a manipulation and grasping challenge, and then there were 3 guys wearing masks dancing in front of a robot, just trying to attract people to do what we are doing. That's us. So we took this robot from Northeastern to Philly and then demonstrated the real world grasp learning on site. So basically what this system do is that there are 2 beams in front of the robot, and then we try to pick up any object from 1 beam and then place the object randomly in another beam. So once all of the object from, let's say, the left beam are all picked up, we switch to the right beam. So this gives us an automatic reset procedure for learning how to grasp. And In fact, this framework can learn with just 600 steps. So we only need 600 grasp attempts to reach more than 90% training success rate. And during testing, on the right, we tested the performance of this package with some novel objects. Those objects are never seen during training, but we were able to achieve over 95% success rate for the testing. And again, this whole procedure happens within 600 grasp attempts, and the walkout time is just within 1.5 hours, which is great. Okay, great. So far, we have talked about Equivariant reinforcement learning. We got great success in using the symmetry in RL. But one drawback is that RL require a reset and reward function. In the real world, this can be very tricky to implement. And also, we have a very high acceleration complexity. Oftentimes, the robot need to do random acceleration at the beginning of training. In the end, we were limited in an SC2 action space. All of the actions were top-down. So in the next project, we try to solve those problems by using a similar Equivariant idea in diffusion policy. So diffusion policy recently has been quite successful in migration policy learning. Instead of learning a mapping from state to action, diffusion policy learn a denoising function that takes in an observation, an action, a noisy action, and a denoising step, and output a noise prediction to perform the denoising. So the advantage of diffusion policy is that we can capture the multimodal distribution in behavioral economy, especially in closed loop settings. Let's say that we wanna, pick up this phone. There are like multiple ways of actually performing this grasp. But standard models, if you just learn the mapping from to action, it's possible that you're gonna end up with the mean of all of the possible trajectory, which might not be good. But the downside of diffusion policy is that we are essentially learning a more challenging function. So before, in standard behavioral economy, we only need to learn from state to action. Now we are learning a mapping from observation, action, and denoising step to noise. This is a larger function space to learn. So if you have ever trained diffusion policy yourself, you might have noticed that the convergence speed for diffusion policy is often slower than the standard learning methods. So, but this is
you don't learn a whole trajectory.
You do need to learn for the whole trajectory. So you mean we generate multiple steps in the denoising process?
No, that's different. But you don't generate incremental steps the way you did it in the first part of the talk.
We do generate incremental
But after
steps.
you predicted the path, right?
Yeah. Yeah. So typically in diffusion policy, we predict, let's say, 18 steps into the future, but we execute 8 of them. So it is still a closed loop setting. So we need to inference the network after 8 time steps. And those 8 time steps could be smaller.
I mean, the output of the diffusion network is not one step.
It's multiple steps.
Case steps, yeah.
It's case steps.
Yeah.
Right? And have you fixed A and B, or do you have fixed A and like path goes anyway?
Sorry, what is A and B?
If you want to go from A to B.
Yeah.
You have fixed A and B.
Yeah.
And you predict the whole thing from A to B, or?
No, yeah, that's a good point. So we do not predict the entire trajectory. We only predict, let's say, 1 second worth of actions. And then we evaluate the network to get another 1 second worth of actions. Yes, so this is a great learning framework. So after reading this paper, one question I was asking is, does symmetry exist in the noise prediction function? Because if so, we will be able to use a similar strategy in diffusion policy to make it accurate, right? So the answer is yes. So here's an illustrative example. Imagine that we are performing, let's say, navigation, and we are at the black dot. We want to get to the green poles while avoiding the blue obstacle. We start from a randomly sampled trajectory, and we iteratively inference the denoising network until we have a noise-free action at the end. Now, if we rotate the state and the initial distribution of the noise, what we want for the denoising function is to rotate all of the intermediate denoising steps so that at the end of the denoising process, we will have the exact same trajectory predicted before, but in a rotated manner. So
But your steps are they're not in configuration space, they're over the obstacle as well.
sorry, can you say that again?
Your steps can be through the walls. They're not in configuration
The
space.
denoising steps. Yeah.
So
The denoising steps can be anywhere, like
Oh.
going through walls.
yeah,
through the floor.
in the denoising steps, it doesn't know about the obstacles, but at the end of the denoising process, we expect the network to learn to avoid the obstacles.
Because I have seen like Jan Peters, like.
Yeah. Oh, yeah.
and
So
others
yeah,
who
we were
do
talking about.
Would do optimization
Yeah.
during.
Yeah,
the
yeah,
test
yeah,
time
yeah.
to be like-
Right. Actually, I just heard from that paper from your student. So, yeah, I do think that's a very smart idea to embed the obstacle avoidance in the denoising process. But I guess in order to do that, we will need to know the geometry or the position of the obstacle in the world. But here we are more like learning into it. So we don't know where the obstacle is. We just have the vision input, and we want to just learn this obstacle avoidance from demonstration. So
How does the network know that there is an obstacle there?
you can see it. So let's say that in the top left state, the network will take in two inputs. One is the state itself, which doesn't have the trajectory. Another input is a randomly sampled trajectory. So because of the vision input, it can infer where the obstacle is in the world.
You need a penalty.
No, we don't need to. We don't need to penalize.
No, it's being trained with imitation.
Yeah,
Oh, that's.
It's being trained with imitation.
yeah. We
The
have.
imitation gives a penalty.
Yes.
Right.
Yeah. I
Sorry,
didn't
yeah,
know,
I should
I
have
didn't-
that, yeah.
I mean, you should have to give the basics, I mean, we are.
Yeah, I apologize.
I mean,
Yeah, this is in imitation learning. We are giving the state action pairs, and we are trying to imitate them. Yeah. All right. So, theoretically, in our recent Core 24 work, we were able to prove that when you have an SO2 equivariant policy that you are mitigating, the noise prediction function should also be SO2 equivariant. Meaning, if you rotate the observation, the noisy action input, the output noise of the noise prediction function should rotate accordingly. So we implement this idea with a similar strategy that we did before and tested it in a bunch of experiments. First, we were looking at some mimic gen environments that involves both simple tasks like stacking blocks to very challenging tasks like coffee preparation, where the robot need to perform the sequence of actions to make a coffee. So we were able to outperform a lot of the state-of-the-art benchmarks dramatically. So on the left, this is a result training with 100 demos. In all of the 12 tasks, we were able to do much better than the diffusion policy, the DP3, which is 3D diffusion policy in RSS 24, and ACT, which is the one using Aloha. And we roughly get around 20% of improvement with 100 demo in all of those environments. And furthermore, if we take an average over all of the environments, what we could do with 200 demo outperforms the baselines with 1,000 demos. So we basically get a 5 times sample efficient improvement. And here you can see there are 2 lines of our method. One is this VO and one is this IN. That stands for the voxel input and image input, that like we discussed before. So here, if we use the voxel input, we can kind of solve the problem of the arm occluding the environment and so on. So basically, we can take the depth RGBD images from multiple cameras and synthesize them together to generate the voxel. Yes.
Sorry, which group were you considering, and like what action space was it for this? Like diffusion policy, I think they presented like multiple versions of like action spaces. That
Yep.
found for like better or worse?
Yeah, that's a good question. So the group that we use is C8 that consider 8 discrete rotations. And then the action space for the robot is the SE3 gripper pulse. So there's a 3 vector for translation, and there's a rotation matrix for rotation. And in the end, there is 1 bit for gripper open and close. So compared to the SO2 Equivariant reinforcement learning here in diffusion policy, we were able to extend the idea to an SE3 action space. But note that we are still using SO2 symmetries. So here we decouple the concept of symmetry group versus the robot action. So we were able to show how can we leverage SO2 symmetry in a higher order SE3 action space.
So the SE3 actions are continuous?
Yes,
Okay,
yes,
okay.
yes.
So is this because of gravity or because of like?
Yeah, the reason we were using SO2 symmetry is mostly because of gravity and the analyze of the ground truth symmetry that exists in the policy function. For the task that we were considering here, I believe there is no SO3 symmetry. So we only consider SO2 symmetry group. Furthermore, we perform another interesting experiment where we categorize the environments into 3 groups. We have the high variance group where the objects are initialized more randomly. We have the intermediate variance group where part of the objects are initialized in certain regions of the environment, but within that region there's some randomness. For example, the mug is always on the left side of the table, but it's randomly on the left side of the table. We had the low variance task where some objects doesn't have any randomness at all, or some object doesn't have any rotation randomness. And because we are enforcing SO2 symmetry in the network architecture, it is expected that our network will do better in the high variance task because those distributions better matches the symmetry that we are embedding in our network. And experimentally, we got the same result. So on the right, the numbers show the improvement comparing our equivalent diffusion policy versus the standard diffusion policy. We were able to see that for the high variance tasks, we can get a more significant improvement. But what's interesting is that even for the intermediate and low variance tasks, we are still better than the standard diffusion policy. That means the symmetry that we embed in the network can implicitly helpful for the policy, even though it doesn't directly match the ground truth distribution of the objects in the world. Great, and we also did some real world experiments like I showed in the beginning of the talk. So we can solve different tasks with very a few data. For example, the big one on the top left, we only need 60 demos, and then there's a copy making task where we need 160 demos, and others were all under 50 demos. That includes a toaster oven task, a pipe screwing task, a drawer cleanup task, and a cleanup toolbox, push trash out of the scene, and so on. All right, so that's all for the third part. And in the end, I also want to talk a little bit about how can we handle symmetry mismatch. Why is that important? So recall that in equivariant reinforcement learning, we were defining the state as a top-down image centered with respect to the picture, right? So that we can use the rotation of the image to represent the rotation of the state. This makes sense, but real-world problems are not always formulated that way. For example, we can have some fixed background, or even we can have a tilted camera angle looking at workspace. So in that case, there will be what we call symmetry mismatch. If you rotate the object in the environment, it's gonna be different from the way you rotate your image. So the object transform on top is what we really wanted, but it is hard to find an equivariant network that can model this object level symmetry directly. What we could do instead is to still use an equivariant model to model the image by symmetry, right? This is simple. We just use whatever we have before. But the problem is there is a mismatch between those two. The rotated object doesn't map to the rotated image. However, in our actual Chinese series spotlight paper, we were able to show that even with this symmetry mismatch, the equivariant model can help you to model the ground truth object level symmetry. And we call this extrinsic equivariance. It is extrinsic because we are enforcing equivariance toward out of distribution data. You are never gonna see this image in your training or testing distribution. So we call it extrinsic, but it is still helpful. So why is that? So far we only have a hypothesis. We haven't like formulated as a theory, but my hypothesis here is that if you have a standard network to learn the object level symmetry, you need to learn a mapping from the unrotated state to the unrotated output and the rotated state to the rotated output. You need to learn from those two things separately. But if you use an equivariant network that models image by symmetry, after you learn from, let's say, a mapping from X to Y, you directly generalize to GX to GY, even though this GX is not the ground truth object transformation. You are essentially turning the problem of learning two different mappings to learning to match those two images. And this matching could be easier to learn because there are similar patterns, right? The duck, even though it's not at the exact same position, it could be easier for the network to find this matching. So experimentally, we were able to show that our method in blue, which is exactly the same as our equivariant stack algorithm that I showed before, we're still able to outperform all of the state-of-the-art algorithms. Even the input is just a set view, very standard set view RGBD image like everybody else uses. So we also observe a similar improvement in the equivariant diffusion policy. So one thing that I didn't say when we talk about the diffusion policy experiment detail is that the image input we use here is not a top-down image, right? This is just a third-person view image. But just using that image directly, we were able to do 11 or 12% better than the diffusion policy. And it's pretty the same improvement across all of the environments, across all of the different number of training data. So basically,
the imitation learning was top down, and the diffusion policy was running. The examples were top down, and the diffusion was running on a tilted. It's the setup, or both were on a tilted.
Everything is tilted. So so both our method and the baselines were using the exact same data set. And the image operations were always like this, the tilted view angle.
But when you write the equivariance equation, it does not hold because the content is different when you look at that from the other side. This is what you want to say, right?
Oh, I see. That applies to the voxel input, but for the image input, the equivariant equation could be validated. So but we can represent the equivariant equation using the ground truth state rather than the image observation, and we expect the network to extract that symmetric, the symmetric visual representation from the tilted view angle. Okay, so to sum up, today's talk we talked about how can we use equivariance in reinforcement learning, including actor-created and Q-learning. And we also show how can we use it in this very new diffusion policy framework. In the end, we briefly talk about how can we handle latent symmetries. Even though we have those symmetry breaking factors like tilted camera angle, we can still use an equivariant network. So key takeaway of this talk is that first, equivariance can really dramatically improve sample efficiency in robot learning. So it's just a very simple change in your network architecture, and you get a great boost in the performance and sample efficiency. And secondly, it's also a very simple procedure. First, what you need to do is to identify the symmetries in your problem, and then you need to find appropriate equivariant network architecture and appropriate way of using those equivariant network architecture. Just with those two steps, you're ready to go. And in the end, we show that the equivariant learning is pretty robust in different problem settings. Across the board, we have reinforcement learning and behavioral learning, and we also have some peak place and grasping that I didn't have time to present today. And even with symmetry mismatch, as in the last section, the equivariant network performance were also very robust. For future works, the first thing I want to do is to keep exploring different ways of leveraging symmetries in robot learning. I believe we only scratched the surface of this area. There are a lot of things that we can still do. For example, for all of the methods I have talked about today, I only use rotational symmetries. There are different type of symmetries that we can leverage. And then secondly, I think I really want to explore the connection between the more efficient model, like what we have in the equivariant model, and the large foundation models. We all know that the large foundation models are taking over. I really want to figure out how can we take the benefit from both of those worlds. And in the end, I would like to explore leveraging symmetries in other robotic problems other than robotic manipulation. For example, I believe similar methods can be applied in navigation or mobile manipulation or even locomotion, but we just haven't explored that yet. I'd like to thank a lot of my co-authors, both in Northeastern and in the AI Institute, where I interned twice, both this year and last year. None of the work is possible without their help. And if you are interested in knowing more, here are some websites. You can scan the barcodes for the Helping Hands Lab, which is Plastic Lab, the Geometric Learn Lab, which is Robin Waters Lab, or my personal webpage. There are more interesting stuff you can find on our website. And I'd like to thank everyone for your attention. I'm happy to take any other questions you have. Thank you.
Thanks for the awesome talk. Our scheduled time is technically over because we have to ask questions during the talk, but let's have a few more. But if people need to leave for another meeting, that's totally fine.
Sure.
Any questions in the audience?
Hi. So for the last problem, the symmetry mismatch, I guess when you have a tilted camera, if you assume that actually you have a to equivariance, as we rotate, we will see like the cube that is on the top of the image will come on the bottom, but with the same size because we don't do any projection. So we will assume that we want the same policy with another image where the cube is actually on the bottom, but because it's the same size, it's a bigger cube.
Yeah.
So even though we have this mismatch on the size, you still observe that the equivariance is better than non-equivariant.
Right.
So rejecting this size mismatch.
Right.
Do you have any intuition?
That's right. So I guess one key thing I want to mention is that we call the symmetry mismatch extrinsic equivariance, right? So it is extrinsic because you won't see this rotated image in your data set. This is important because if the rotated image is part of your data set, your network is going to be confused. We actually have another paper that discuss what's going to happen if you have this type of confusion. For example, if you use the rotation environment network to classify digits, it's going to confuse 6 and 9. But in this extrinsic case, you won't see this rotated image in your data set. So it's not going to confuse network. That's the first thing I want to clarify. The second thing is that even though the cube right there are smaller, the cube down here will be bigger, the network can still match them because spatially they are close to each other. Because if you rotate the object versus rotating the image, the cubes might exist in a similar range of positions.
So I guess the assumption for this improvement is that, yeah, we will not see the transforming.
Exactly. Yeah. Yeah.
I guess, I was wondering, if you have thoughts on like, the actions, like, what is a good action space? Since it really affects the, like, kind of equivariance you want from your network, like.
Yeah.
I mean, I think there's one work that you didn't mention, that was exploring like this manifold or like this distribution, like generating a distribution of like transposes.
Yeah.
That
Yeah.
differs a lot from like the delta velocity or
Yeah.
delta pose, like, do you have any thoughts on like?
Yeah, that's
what action space?
yeah, that's a great question. I don't think I have a very clear answer to that. I think a lot of things are related with each other. For example, like you said, different action space and different symmetry that exists in the action space are related to each other. And also the problem also plays a role here. For example, the grass distribution work that we talk about individually work, predicting just a single grass pulse or sampling a grass pulse from a set of grass distributions. But if you directly apply it, let's say in diffusion policy, I don't think it's gonna work. It's not gonna give you, let's say, a distribution over noises. Maybe it could, but I think it's not trivial. So I would say, it really depends on your problem setting. So for example, if you are in a problem where you don't really care about recover from failures, you care more about just get the task done, maybe this, the second part, the Q learning framework where you have the Q map and execute the peak place action directly, maybe that will be better. But if you really care about the dynamics, the interaction between your gripper and the environment, maybe you will need the first one. Yeah.
Okay, I can ask a question.
Yeah.
What is the advantage of using the discrete groups instead of continuous groups?
Oh, yeah, that's a great point. So we were mostly using I was mostly using ESE as the backbone for my Equivariant architecture. And then I believe the so-called regular representation was the best hidden layers for that network architecture. So only discrete groups have regular representation.
Exact regulars.
Oh,
Exact regular representation.
yeah, yeah. If you can have
Actually,
some.
only D4 has exact.
Huh?
Regular is the warping of the image.
Hmm.
The representation when you warp function. The only exact is the 90 degrees.
Okay.
Not even 45 or.
Gotcha. And is that related to like when you rotate the image, some things are out of frame? Is that?
No, you have to interpolate.
Yeah.
So it is not exact.
Gotcha, okay.
Yeah.
If you rotate 10 degrees, you have to interpolate it.
Mhm. Right, okay, like the cells don't line up, you're saying, got it, yes.
Yeah, and there's another reason, which is I think the marginal effect. For example, if you have a symmetric problem that is SO2 equivariant, right? So if you use a C2 equivariant network that only consider 180-degree rotation, you're gonna cut down your problem size by half, right? But if you further make it C4 equivariant, you only get another improvement of 1/4. And if you make it C8 equivariant, get another 1/8. So the improvement you get is fewer and fewer, but every time you double the size of the network. So I think just from the original authors, they also found the D4 or C8 for like the sweet spot.
Okay, thank you.
Sure.
So in this paper, you really mean that the duck is almost like has like a 180-degree symmetry, or what do you mean by latent symmetry?
Oh, latent symmetry means this we cannot define the group action on the input directly. We cannot explicitly write down like the top-down images, we can just write down the image rotation and use it as the state rotation.
Like this is a function of that image alone. We
Yeah.
can't construct the rotated image.
Yeah. We cannot explicitly construct this rotated duck from an unrotated duck. So that's why the symmetry is latent from the image's perspective.
Yeah, because you have to hallucinate the pattern.
Yeah. Not only that, maybe some, for example, if you only see the front face of the duck, you don't really see the backside of the duck. So not just, hallucinate the duck.